I want to review briefly some main points we went over last time. We're thinking of machine learning as learning a function. And depending on what kind of function you learn, we give a different name. You have the input, the type of output, and then maybe we have a performance measure. The input comes from the technical domain known as anything. The output is what matters. If the output is categorical, we call it what? Classification. I'll add a name here. When the output is real, we call it regression. When the output is probability, namely a number between 0 and 1, we typically call it logistic regression, although it's not necessarily the best name. And we talked about other things like planning. I want to talk a little bit about a performance measure. What performance measure might we use for classification? Percentage classified correctly, or equivalently percentage classified incorrectly, or error rate, all the same thing. If the outputs are truly distinct categories, they have nothing to do with each other, that's kind of the only measure. Sometimes making one kind of classification error is more egregious than making another kind. So you might slap another matrix on top of that, a confusion matrix that says how bad is it to confuse A for B, how bad is it to confuse A for C, and so forth. It's variations on the same idea. Sometimes the categories are not really distinct categories, they come from a hierarchy. So misclassifying a document about baseball as if it were about football is not the same as misclassifying it as if it were about science. But for the most part, we're counting errors. Performance measure, we'll call it percent correct. Or maybe weighted. If some errors are more serious than others, then we will weigh them. What about regression? How do we measure our performance here? Error. Well, more specific. Sum of errors. Some mean squared error. Other suggestions? Sum of squared errors. Any other possibilities?
Norms.
Sorry?
Norms.
Norms. Okay, that's the general description for it. So by far the most commonly used measure is sum of squared errors or mean squared error, which is kind of the same thing, right, up to constant. So there would be sum of the output of our function minus the true value raised to the power of 2, averaged over all possible training examples, so it's normalized across different test set sizes. And this would go by the name of mean squared error. If we forgot to do this, it'll call it sum squared error. Is this the only thing we can do? Absolute error, why not? What's wrong with this? F of xi minus yi call it mean absolute error. Anything else? Yeah? Maximum error, I love that. How about maximum absolute error? Right? Any other possibilities? Root mean squared error. So that means coming here and doing this. What would be the difference between using mean squared error and root mean squared error as our measure of performance? Would it lead to different outputs, different functions being learned? Are there some functions that are better on mean squared error but less good on root mean squared error, and vice versa? I forgot to mention you have to wake up before class, not after. Is it possible that there would be two functions, f1 and f2? One of them has a better mean squared error, f1 has a better mean squared error, f2 has a better root mean squared error? I need to see a lot more heads doing this. No, it is the same measure, really. Yeah, convince yourself. If the mean squared error, if x, well, not call it x, if z1 is less than z2, then square root of z1 is less than square root of z2. So mean squared error and root mean squared error kind of measure the same thing. Why do we sometimes use RMSE? We call it RMSE. We'll talk about it in a minute. Let me come back to this question of mean squared error versus mean absolute error versus maximum absolute error versus something else. First of all, is there something else? Mean absolute percent error. I like that. So percent error, also known as relative error, is the error weighted or as a fraction of the true value. So 2.01 as an answer to something, the answer to which should have been 2, has a 0.1 error, and 175.1 as an answer to something that should have been 175 also has a 0.1 error. But you may argue that 2.1 is a bigger error relative to 2 than 175.1 relative to 175. Okay? So you might care about the relative error, so that would be a relative error, and we could take the absolute value of that and do the usual thing. So this is mean absolute relative error or percent error. Let's stay with these. We used absolute error here. We used squared here. Why squared? Why not cubed? Can we use cubed?
Cubed would be the negative and it wouldn't be the absolute.
Okay, so how about cubed of absolute? So just to make it uniform, I will put absolute here on everything. And I will ask you this. If you are about to measure error like this, to the power of p here, what value of p would you use? You gave me already p equals 2. That's the mean squared error, or root mean squared error. You gave me also p of 1. That's mean absolute error. Why not p of 1.732? First of all, can you? Yes, it's a free country. You can do anything you want. You can absolutely do that. The question is, what does it mean? What will it lead to? Why are we using 2? Let me give you two answers, and you may have others. One is a pragmatic one. We're trying to minimize this measure, and often minimization goes through taking a derivative and equating that to 0. If you take a derivative of something like this, you get a linear expression. All right, derivative of a quadratic of a second order polynomial gives you a linear expression which would be maybe easier to solve analytically. It's more like searching for what you lost under the light. It doesn't say that it's a better measure. It says it's a measure that's easier to optimize. But there is a much more fundamental reason for that, and that is that often a squared error corresponds to an assumption, either hidden or explicit, that the error is Gaussian. Or rather that the error is Gaussian. And let me give you a brief peek into why that's true. Brush up on your Gaussian. A variable is distributed as Gaussian with some mean and some standard deviation if the probability of x take on specific value is 2 pi sigma e to the negative x minus mu squared over 2 sigma squared. Does that look familiar? It should. If you take the log of that, you get a quadratic expression. So the log likelihood of a Gaussian is quadratic. We will see later a deep relationship between log likelihood and error. Okay? Just store it away somewhere. We'll come back to it. That doesn't mean that L2 is the better measure. It just means it corresponds to a specific assumption about Gaussian noise. Maybe your noise is not Gaussian. So I gave you two reasons. None of them are very good. One is that it's easier to take a derivative of, and the second is that it corresponds to Gaussian error. Now, which measure should you use? Should you use p equals 2, p equals 1, or something else? Which is the right measure to use? Louder, please. Thank you very much. You've hit on my favorite answer. It depends. Depends on the problem. If any of you have watched my videos before, it will not come as a surprise to you. Anybody who says it depends as the beginning of their answer automatically gets points. But you need to qualify it with depends on what and why. So, okay, so what does it depend on?
For example, you either have an option that the data is constant.
Okay, so the answer was, for example, if you have reason to think that the noise is Gaussian, then you should use L2. Then you should use p equals 2. Okay, what else could it depend on? It depends on the range of errors. Why?
So we have a function of which errors will be somewhere between 0 and 1. The square measure will only tell that it's a very low error. But on the other hand, if we have an absolute measure to that, the value says that it's compared to take this. If you compare the error function outputs in these two cases, using one absolute and one a square, you get different results. So how do you want to maximize or amplify your error?
So you're suggesting that in cases where the error is restricted to values between 0 and 1, the choice between using square or not using square, using another value of p, might be different than if the answers are larger than 1. Well, let me give you a hard time a little bit. Suppose the answers are between 0 and 1 because you measured them in kilometers. But tomorrow you're coming back and measuring them in meters. And all of a sudden something that was between 0 and 1 is now between 0 and 1,000. Should that change your decision of what to use?
A generalized program shouldn't.
It shouldn't change. So it's not the fact that it's between 0 and 1 that makes a difference, because this is somewhat arbitrary. Now you're right that when you take a number between 0 and 1, you square it, you get a smaller number. But the overall relationship between different functions on the value of p will not change whether the values are between 0 and 1 or not. If you multiply all the values by 1,000, the relative ranking of performance of different functions would remain the same. So what else would you consider in choosing a value of p? Yeah?
You could consider your own computer resources.
Your computer resources?
If you
Okay.
have hardware that's optimized for certain algorithms.
Okay. Fair enough. All right. Let's keep it on hold and look at other solutions. What else should you consider? Yes? Thank you. Thank you. The answer is how much you care about larger errors. So the main thing you should consider is what is it that you're trying to achieve? In all cases, you're trying to achieve a function that's as close to accurate as possible. But in regression, we're never looking for a function that's exactly right. Right? Unlike classification, where you're trying to be exactly right. In regression, it's always about how close to the truth you can be. And what matters is your definition of close. And how you're going to take into account errors on different possible inputs. So would you rather be very close on most things, but way far on a handful? Or would you rather be as close as possible on all of them together? So it's a little bit of, are you a socialist or are you a capitalist? Are you trying to maximize the overall GDP of the population, or are you trying to minimize inequity, to minimize, to sort of treat things more uniformly? What's the extreme case of a socialist? P equals 1. Someone suggest something else? So a socialist would be someone who doesn't care so much about the average. They wants to make sure that everybody has some minimum, right? Everybody can live, everybody can eat. P equals infinity, which corresponds to the max, which we have here. So this is something worth knowing. If you take the usual measure of and you take that and you raise it to the power of 1 over p, where does it go? Well, for p equals 2, this is root mean squared error. This is the square, this is the root, right? For p equals 1, this is mean absolute error. This didn't do anything and this didn't do anything. For p equals infinity, this is max. And the other extreme, what happens with p equals 0? So p can never be infinity, it tends to infinity, and similarly p cannot be 0 because of this, but it can tend to 0. P tends to 0. Want to think about it a little? You get the number of errors. Number of non-zero terms. More of interest to us is the range in between. P being a small number, 1, 2, 3, 7, 2.5. It could be a fraction. And the main reason to choose is what do you want to achieve? What do you consider successful? And there could very well be two functions, one of each is better on P1 and the other one's better on P2, and it's up to you to decide which one do you like better, which one do you want to work with. Now, why are we doing this? I mentioned before that in the case of p equals 2, that taking the root does not make any difference to the optimization. The optimization problem is the same, whether you call it mean squared error or root mean squared error. Why would we do this? The answer is to stay in the same units as the original. So if the original thing we're trying to measure is length, and it was measured in meters, mean squared error is measured in meters squared. Root mean squared errors is measured in meters again. Okay, it's a question of units or dimensions. If you are using a norm like this, and this is called an LP norm, if you're using a norm like this or a performance measure like this, if you want to compare apples to apples, if you want to compare an L2 norm to an L1 norm to an L7 norm, you should raise it to the power of 1 over p so that the result is expressed in the same units. It's meters squared, it's meters as opposed to meter to the power of 7. But it's not necessary if you fixed yourself on a particular p and you're just trying to find the function that minimizes it, then it doesn't matter if you raise it to 1 over p or not. It won't change which function minimizes it better. Questions? All right, let's continue here a little bit. This was regression. Do some experiments here and not producing noise. Okay. When you learn logistic regression, what should be your performance measure? Logistic regression is the learning of a probability. How do you know that you learned good probabilities? Louder, please.
We set up a threshold.
You set up a threshold. Okay, what do you mean by that?
For example, the probability is over 50%, then we know that the function is learning correctly.
You're saying that if the output of our function is over 50%, then we know we learned correctly? But what if the event we're trying to learn is truly rare and we assign it a probability of 10% correctly? All right, you're a loan officer again, and you get loans, and it's your job to estimate the probability of default. Some of them you're confident are very good, and you give them a probability of 2% of default, and some of them are very shady, and you think they have a 60 or 80 or 90% probability of default. Suppose we have enough time to see what happened with them. Some of them defaulted, some of them didn't. You are one loan officer, there's another loan officer sitting in the next cubicle, and they have a different estimate of probabilities for all of these. 5 years passed, the loans have either been defaulted on or paid back. How do you tell which one of the two of you had a better estimate of the two probabilities? Let's start with the simplest case. Suppose there was only one loan application. You, your so-called friend, outcome. All right, you said there was a 0.2% chance it'll default. Your friend said there was a 0.3% chance it'll default and didn't default. Who was more accurate? You, that's me. You, Mr. You, Dr. You here. Yeah, who was more accurate? This guy was more accurate because he said there's an 80% chance that this will happen. And this guy said there's a 70% chance that this will happen. Was this guy wrong? No. Was he wrong or right? No. When we deal with probabilistic prediction, there's no wrong and right. Okay, that's an important point. In classification, there's definitely wrong and right. In regression, technically there's wrong and right, but practically everybody's wrong. It's a question of how wrong they are, right? In logistic regression, there's no wrong and right. There is more accurate and less accurate. So let me write this a little bit differently. I will write not just the 0.2, but also the 0.8 here. And not only the 0.3, but also the 0.7 here. So that says 0.2 chance of default, and here's not default. Default, not default. And then what actually happened was no default. So what happened was no default. I said there was an 80% chance it would happen. My so-called friend said there was a 70% chance it would happen. I score a little bit more. Here's another loan. I said there's a 20% chance it'll default and an 80% chance it will not default. I said the same thing. And my friend also said the same thing. And this time it defaulted. Who won this one? My friend, okay? My friend won this one because what happened was the thing on this side. I gave it 20%, he gave it 30%. So the general principle is we want the things that actually happened to have been given a high probability by us, higher than somebody else, right? Now suppose both of these things happened. There were two cases and we are being judged by our supervisor. Which one is better? Are they the same? The 0.1 difference, one's this way, one's that way? Relative error. How do you define relative error?
0.3 minus 0.2 over 0.3.
You're suggesting 0.3 minus 0.2 over 0.2 or 3. So what you're implying is that one of us should be treated as ground truth, and you see how close the other one is to them. Okay, but what if there's a third loan officer and they assigned, here's the third one, they assigned 0.1 and 0.9, and here they assigned something else, 0.5, 0.5. I need to be ready to compare any set of predictions, probabilistic predictions. Yeah? Go on.
Better when you measure with the likelihood.
So you're suggesting that we measure likelihood.
Like when it's the first case, like you said it's not default, so it's 0.2, and if it's default, it's 0.8. So 0.2 multiplied 0.8 is...
Okay, thank you. I like that. Let me just rephrase it for our television audience. What you're saying is focus on the likelihood that I assigned to the entire sequence of outcomes and compare it to the likelihood that my friend assigns to the entire sequence of outcomes. The likelihood that my answer, my estimates, or my probability estimates apply to the actual complete set of outcomes. According to me, is this happened, and I said there was an 80% chance it will happen, and then this happened, and I said there was a 20% chance it would happen. Assuming that they're independent, That's a big assumption, often holds in our examples, but we have to remember that's an assumption. Assuming they're independent, the likelihood, or at least assuming that my model of them is independent, I claim that they were independent, then the likelihood of what actually happened, according to my model, is 0.8 times 0.2. Whereas the likelihood of the exact same thing, according to my friend, is 0.7 times 0.3. So usually, almost always, in learning probabilistic predictions, I will use the likelihood of what actually happened as my criterion for who's more accurate. I don't have to. Just like in the case of regression, I have a choice. I can think of other measures. Having this measure, using this measure, will make a difference. If I use a different measure, I may end up with something else. But this is by far the most commonly used measure. Big difference between this and error. Error is bounded. You can't have error less than 0. This is bounded too. What's the highest value I can have here? 1. But in classification, at least, the error of 0 is something I can aspire to. Here, what does it mean to get 1? It means that I knew in advance exactly what would happen every time, right? Not realistic. So here, even if my number here is very far from 1, it doesn't mean it's a bad assessment. If I have a fair coin and I flip it 10 times, and I try to estimate the probability of each one of the outcomes, if it's really a fair coin, the best I can do is say 50-50. And whatever the outcome is, it'll be 1 in 1,024. The likelihood would be very small. It doesn't mean my model is bad. There is an upper bound here that is tighter than 1. It has to do with the intrinsic uncertainty of the process. When we talk about information theory, we'll call it entropy. All right, so I will complete this here with likelihood of actual outcome. Or outcomes. How do we measure a plan? I don't know. It's a lot more complicated. You know, how useful it was to you, how fast you got there, cost. There are many more choices there. It's a lot less clear. I mentioned one other paradigm of machine learning earlier called density estimation. If you remember, density estimation is also learning a probability, but it's not learning a probability of outcome, it's learning a probability of the input itself. We use the same likelihood principle there too. The better model is considered the one that assigned a higher likelihood to the actual training data or test data. Okay, any questions before we move on? Yes, please.
So with this last example, why would you take your final likelihood and raise it to the 1 over n power to get it back into something that doesn't just keep getting smaller and smaller?
Wonderful, wonderful observation. Thank you. So we saw that in the case of the LP norm. Yes, I will just repeat the answer. I will just give the answer. It would give the question. I'll give both. In the case of LP norm, thank you, Daniel. In the case of LP norm, we were careful to put a 1 over n here. And I think I mentioned that it really doesn't matter for the purpose of finding the better function because n is a constant. But it matters if you compare test sets of different sizes, right? You want to look at the average behavior, not at the average error, average, with some power. The question here was, why not apply the same idea to the likelihood? So I gave an example with 2 applications, but what if you have 1,000 applications? If you have 1,000 applications, even if you do a very good job of estimating the probability of default, you're going to have a product here of 1,000 numbers. That's going to be a tiny number. You're going to look really bad and get fired, right? So the answer is yes, absolutely, you should do that. And exactly the way you suggested, which is raise it to the power of 1 over n. You will see it often in a slightly different form. What you will see instead, can you guys see from there? Maybe I'll put it here. Let's take the likelihood of the outcomes, likelihood of outcome 1 through outcome n, given your model. Often, we would be in a situation where the outcomes are independent of each other, and therefore we can write it as product of the likelihood of outcome I given your model. And what the gentleman was suggesting was that we take this to the power of 1 over n, which I think is a good thing to do. Again, it doesn't matter if you have a fixed test set, if you're comparing different functions on the same fixed test set, but if you're comparing across different test sets, you're trying to compare apples to apples, you should normalize it that way. When I said you see it in a different way is because often we work not with likelihood, but with log likelihood. Likelihood being extremely small numbers. Log likelihood given your model is a log of this, and the log of this can become a sum of log of individual elements, and then the 1 over n here becomes 1 over n here. And this goes by the very apt name, average log likelihood. Thank you. Other comments or questions? Okay, so we're going to now focus on just one type of learning, the simplest type, and that is classification. I'm not suggesting classification is easier than regression. In fact, in some senses, it's harder. But I'm going to focus on the simplest type of classification, which is classification into just 2 classes. That's called binary classification. To remind you, all the names have to do with the output, not with the input. So binary classification doesn't mean that your input is binary. It could be anything. Binary classification means that your output is binary. There are only 2 possible outputs. So our problem for the next lecture or 2 is going to be learn a function from some input, which I will call x, into 2 categories, or 2 classes, category 1 and category 2. Because there are only 2 categories, I only need one name. I don't need the name for category 2. I can just call it not category 1, right? Not category 1. And the next step beyond that is to call this yes category 1. And then for short to just call them yes and no. Okay? So yes or no, black or white, up or down, it doesn't matter. Mathematically, they're equivalent. In fact, mathematically, it doesn't matter which one of them you call yes and which one of them you call no. We could have chosen category 2 and not category 2. So in the general case, we're just going to have a yes or a no Sometimes we will have a true or a false, but that's confusing because that really implies some morality, like this is better than this. 0 and 1, Green and Paris. Okay, they don't have to come from the same semantic category. Two names. Mathematically, they're all the same. So this is a binary function. We're learning a binary function. And now there are other ways of representing binary functions. I want to go over all of them because I'm going to switch between them all the time. One way of thinking of a binary function is what is the set of all inputs for which the answer is yes. Instead of saying for any input is the answer yes or no, saying what are all the inputs for which the answer is yes. If you represent all of your inputs abstractly as a set of all inputs, all possible inputs. So the word possible is important here. I'm not drawing here a training data set or a test data set or any data set at all. I'm drawing here the list of all possible inputs, the space of all inputs. Okay? That's usually a much larger space than the actual any one data set, even a large data set. If these are all the inputs, and some of them the answer is yes, and some of them the answer is no, I can try to cluster together all the ones for which the answer is yes, just by moving them around in this square, because I drew the square, I can put them anywhere I want, and just put a line around them, and say, this is the subset of all possible inputs for which the answer is yes. Learning that subset is the same as learning the binary function. That's kind of trivially true mathematically. So learning a binary function is the same as learning a subset. Of all possible inputs. Or I'll call it of the input space. A binary function is mathematically the same as a subset of input space. Suppose I want to learn the concept of a funny story. Normally when people learn the concept of a funny story, it's a really difficult thing to learn. You have to hear a lot of stories, you have to develop a sense of humor, you have to decide what... Mathematically, the concept of funny story is much easier. There is a input space of all possible stories. Very, very large, maybe infinite. And learning what a funny story means is equivalent to learning a subset of that space that is deemed funny. Or alternatively, learning a function that given a story tells you whether it's in that subset or not, whether the answer is yes or no. I'm using different language interchangeably, deliberately, to make the case that a binary function over some input space x, big X would be my symbol for input space, is the same as a subset of X, which is the same as a concept in X. These are all slightly different ways of thinking or representing the same concept. Now, when we talk about concept in everyday language, we have something much deeper in mind, like the concept of a dog. You know, everything you know about what it means to be a dog, including your DNA and their behavior and their look and all of that. From a mathematical or machine learning perspective, the concept of a dog is simply the subset of all possible inputs that is deemed a dog. And what does it mean to learn what a dog is? It means to be able to tell for every input whether it's a dog or not. Okay? We operationalize the notion of concept. It's not the same notion as in everyday language. It doesn't mean we really understand what a dog is. The same is true for if you say, this program learned to recognize dogs and images. If you were not a geek, if you were your mother or your great uncle, and you hear on the news that researchers managed to teach a computer to recognize dogs, you may conjure up these images of the computer finally getting this idea of petting the thing. And no. It's a very operational, dry thing. It's just learning a binary classification. So learning this is the same as learning this is the same as learning this. One more representation, the fourth one, that's a little bit harder. I can try to enumerate the output of the binary function on all possible input. For real-world problems, the possible inputs, there's so many of them that I cannot write it all down. But conceptually, I can at least try to do that. So let me do it right here. X1, X2, well, I'll start here. X1, X2, all the way to X with the last index is going to be big X with bars, the size of X. Okay? So this is an enumeration of all possible inputs, not only the inputs I happen to see, not only the inputs in my training data or my test data, all possible inputs, each one represented exactly once. Okay? This is the input space. How many are there? As many as the size of big X. This is big X. And now I can list here the value of the function. I'll say that X1 is, let's say the task is learning to recognize images of dogs. You know, looking at an image, whether the output is a dog, whether it contains a dog or not. And let's not worry about borderline cases where it contains only the whisker of a dog. But let's just assume that there is a function out there that tells you yes or no whether there's a dog in the image or not. Well, that function would assign 1, there is a dog, to x1, and maybe 0 to x2, and 1 to x3. And it would assign some value, 0, 1, to every possible input. Okay? I'm not saying that's the right function or a good function. I'm saying it's a function. Now, there may be another function. So I'll call this FA, and here I'll call FB. And it might agree with this function on most outputs, but not on all of them. So let's say here it says 1, and then the rest are the same. My point is that you can represent binary functions as bit vectors. As bit vectors, the length of which is the size of your input space. So that could be extremely long, and in some cases could be infinite. But it's very useful because 2 bit vectors that are identical are the same function. And conversely, if 2 functions are not the same function, then they must differ in their bit vector representation, at least in one point. So you can think of the bit vector as another legitimate representation for functions. And the space of all possible bit vectors of that length is the space of all possible functions. Binary functions. A bit vector of length x. These are all the same. Sometimes it's easier for us to think in one of them than in the other, but we should be able to move between them. How many bit vectors are there of this length? Two to this number, right? So if I gave them indices, let's start with 1. And if I list all possible bit vectors, the last one would be f to the 2 to the size of the input space. If I were a true computer scientist, I will start with 0. And then the last one will be 2 to this minus 1. Let's think of a specific example. Let's say I want to learn the concept big cities that I love. As of last year, there were 538 cities in the world that had more than 1 million people. So let's say that's my input space. I'm only concerned with big cities. Concept. Big cities I love. The input space is New York, London, Beijing, Mumbai, the size of the input space is 538. I can represent this concept, this particular concept. I'm not talking about learning now. I'm just talking about representing the concept in several ways. I can draw a box of all cities, all such big cities, of which there are 538, and I can put a circle around those that I love. That's subset. That's a subset of the cities that I love. The second thing I can do, or the other thing I can do, is a function that, given a big city, produces as output love or A. And the third thing I can do is enumerate those cities, city 1, city 2, all the way through city 538. And right here, love, 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 A, A, A. That's a bit vector, even though I'm not using bits, I'm using letters. It's all the same concept. Now, let's move on to learning this concept from examples. For this, I need to know how big is the concept space, namely, how many concepts are there? How many concepts over X are there? And the answer is as many as there are bit vectors over X, right? And that's 2 to the power of 538. So that would be the size of the concept space, which I will call big C, is 2 to the power of the input space, the size of the input space, which is 2 to the 538. If you like to see it in decimal numbers, we can turn it to about 10 to the power of 538 divided by 3.2. I think I calculated this once. It's about 168 here. 10 to 168. Who here knows the number of elementary particles in the known universe? Not exactly, plus minus 5. Plus minus 5%? Yeah?
10 to the 80.
10 to the 80. Oh, were you sitting in my class last year? Okay. Yeah, that's true. I mean, that's my answer. I mean, people have a range of answers, but the range varies from 10 to the 70 something to 10 to the 80 something. So we can actually estimate that from Avogadro's number, the number of atoms in like a gram or so of something, and then the size of the Earth, and then the size of the sun, and then the number of sun-like objects in our galaxy, and then the number of galaxies in our cluster, and so forth. You can multiply all these things together, and you get to about 10 to the 80. So this is slightly bigger than the number of elementary particles in the universe. In other words, it's huge. Okay? And this is a simple problem with an input space that's very easily enumerable. It's 538 is a small number. So the take-home message is that even for very, very simple problems with very small input spaces, the number of possible functions is astronomical. Literally. So we have a problem. How are we going to find the one function we're after if the space is so large? We're certainly not going to find it by considering explicitly each member of that space. Right? There are way too many of them. Way too many. Let me try one more example. Suppose we want to learn to recognize dog in images. Learn image contains dog. So it's a very simple concept of binary classification. Given an image, is or is there not a dog in it? How big is the image? Let's say very modest, very simple, 100 by 100. The image is 100 by 100 pixels. You want to learn from color images or black or white images? Let's say color. Let's live large. So color, RGB. The input space, let's say first the size of the image. So the size of the image in bits, 100 times 100, that's 10,000, right? Times, how many bits does it take to represent every pixel? There are 3 colors, RGB, and each one of them is typically represented by 8 bits. That's typically called 24-bit color. So 24 bits. So we have 240,000 bits. This is the size of each image. This is the number of bits needed to represent every possible image. What is the input space to our problem? The input space is the space of all possible images. Right? How many images are there? Input space is 2 to the 240,000. That's even larger than that number. This is our input space. Let's convert it for you decimals to 10. It's about 10 to the 75,000. That's just the input space. What about the concept space? Concept space for binary concept is always 2 to the power of the input space. So we have 2 to the 10 to the 75,000. Is this the same as 2 to the power of 10 to the power of 75,000? Wake up. Is it the same as 2 to the power of 10 to the power of 75,000? No, it's a little bit different. It's a double exponent. Treat it with respect. It's like larger than we can imagine, really. It's huge. And this is just for learning the very simple, everyday first homework assignment. Learn a dog. Learn to recognize a dog in an image of 100 by 100. 100 by 100 is not a very lot. It's a small part of your smartphone. You know, it's like a little. If you take out your smartphone, it has several hundred by several hundred, what, 600 by 1,000? I don't know exactly. So this is like a small part, okay? Like in the corner, like a little icon. To learn if there's a dog there or not, you have to consider this many possible functions. I have to choose one of them. That's the best one. How in the world are we going to do that? All right, to summarize, the concept learning framework. You have an input space X. You have a concept space C, such that C is always 2 to the X. You have a target concept little c, that's a member of big C. So it's one member of this vast empire. And little c is a concept, meaning it's a binary function, meaning when you give it some input from the input space, it produces as output 0 or 1. It's a binary function. One of this many. Our goal is to find it. What are we going to use in order to find it? We're going to use training data. Training examples consist of the following set of ordered pairs. Some particular input x1 and the correct label for it. The correct label for it, whether it's yes or no, 1 or 0, I can write as y1, but by definition the correct label is the label produced by the target function. So I can also write it as c of x1. This is my first label training example. And I can have x2 and c of x2. This is a little c, this guy. All the way to x little n and c of x little n. And then close the set. This is the representation of my training example. And now my goal is to use these training examples to somehow narrow in on the correct function. All right, let me use the last few minutes to tie this into an example in Tom Mitchell's book, which we will use in our next lecture. The concept learning problem is called Do I enjoy sport? The idea is that given some description of the weather conditions outside, the function tells you whether I'm going to enjoy playing sport on that day or not. Okay? And the weather conditions are given in the form of attributes, which are these attributes up to here. There are 1, 2, 3, 4, 5, 6 attributes. The sky, the temperature, humidity, wind, water temperature, and the forecast. And these attributes are mostly binary. One of them is trinary. So the sky could be sunny, rainy, or cloudy. You don't see it in the examples here, but I'm telling you, and it's in the book, the sky could be sunny, rainy, or cloudy. The temperature could be either warm or cold. Humidity could be either normal or high. Wind could be either strong or weak. Water could be either warm or cold, and the forecast could call for more of the same or for some change. So there are 6 attributes on which we have to make our decision, which are the input to our problem. 5 of them are binary. 1 of them has 3 possible values. This is the space in which we're going to learn the function, a binary function, a concept of do I enjoy sport or not. What you're seeing here is just 4 training examples. You're seeing this. 1, 2, 3, 4. Now let's do a little bit of math for the enjoy sport problem. What is the size of the input space? How many possible inputs are there? Yes? 2 to the 5 times 3, right? So the input space is simply 3 possible values for the first attribute, 2 possible values for the second attribute, and so forth. So 3 times 2 to the 5 is 96. It always comes to 96 every year. So that's the size of the input space. Very small input space. You can actually enumerate it, right? Very easily on the board. If I didn't want to bore you, I would do that. What about the concept space? How many concepts are there? How many possible solutions are there? Always 2 to that. That's a large number. Okay? It's about 10 to the 30, roughly 10 to the about 30. You could not enumerate that size space in your program. I mean, these days with very fast computers, maybe you could enumerate it once. It would not be easy. How many training examples do I have? 4. How in the world are we going to do that? Maybe we want to use 4, maybe we need more. How many training examples do people use when they learn? Sorry? 4? Yeah, that's about right. 4 plus minus 2, right? So think about a young child learning the concept of a dog. Okay? Maybe they go on a walk with their parents for the first time, kind of barely walking, and they're outside in the street, and the father or the mother points to a thing and say, "Hey, Junior, look, there's a doggy." And Junior says, "Doggy," or something like that. And that dog might be a little black thing, fluffy, very nice and friendly. And they keep on walking, and they get to a big German Shepherd. And the other parent says, "Hey, look, another doggy." And the kid says, "Doggy," okay? N equals 2. They keep walking, they get to another dog, that is only partially visible, and it's yelping, it's not barking, okay? And it's not the same size as the other dogs, and it's not the same color, and the kid says, doggy, okay? N equals 2. How do they do that? They keep on walking, and they see a cat. And the kid says, doggy. And the parent says, no, that's not a dog, that's a cat. And the kid gets it. And the next cat they see, they know is a cat and not a dog. N equals 3. Now seriously, how do kids do that? They are searching a space of, how much did we say? 2 to the 100,000 to the 75,000, something like that? I mean, their image is much bigger than 10 by 10, right? And it's video, it's got sound, it's got, so the size, the input space, I'm not completely joking here. The input space is much larger, exponentially larger than the input spaces we considered here, and therefore the concept space is doubly exponentially larger. How are they searching it? They must be doing deep learning. I'm asking you seriously, how are they doing that? How are kids, or people in general, able to learn with so few examples when mathematically the space they're searching in, at least conceptually, I'm not saying they're explicitly searching it, but conceptually the space they're considering is so huge. It's not even huge, it's 2 to the power of huge.
They end up identifying the most predictive features. So they might see something that's fuzzy in 4 legs.
Okay, so they are identifying the most informative features. That's good. That's a good start. They notice that it's fuzzy and it's got 4 legs. So a few questions here. First of all, they had to learn these notions of fuzzy and 4 legs. And somebody had to tell them that these are useful things to learn. And they don't even have the word for it. They may not have the word for fuzzy, but they may understand the concept. The second question is, there are so many potential features. How do they know which features to settle on? How many features, potential input features are there in these images? Sorry? Lots. Actually, there's an exact answer. As many as there are binary concepts. Every binary concept is a potential feature. So by saying you first learn features and then you learn the output based on the features, you are begging the question, because how do you learn the features? Yes?
I think for kids, they have some pre-knowledge, like they already learned, like it's an animal, and right now you add more constraint, like if it has certain features, then it's a dog. So you only have 2 samples, but you could help a kid learn what a dog is, depending on you have some pre-knowledge of the word.
I like that, and it's related to your answer. I didn't mean that the answer was not good. I'm just trying to show that it didn't completely solve the problem. So the answer here was, we don't learn things from scratch every time. We learn in a hierarchy. We learn first, say, the concept of an animal. And then once we have good, settled down and understood the concept of animal, we learn the concept of a dog, which is a subset of animals. Not all animals are dogs. And I would say we start even before that. We learn objects. In very early months of life, children learn the notion of what an object is and the fact that object has permanence, namely that because they perceived it somewhere in their visual field and they don't see it in the visual field, it doesn't mean it disappeared. It's still there if they move their head back or if somebody took it out. So object permanence is a very important stage of learning for young children. So there's certainly some truth to that. There are a lot more things that come into play. So we will spend just a few more minutes talking about it next time. Think about it. Think about what is it that helps people learn, because it's going to be extremely relevant to helping machines learn. Thank you.